appreciate your joining us and your enthusiasm. I'll talk about the speaker in just a second. First of all, speaking of the Quimper Geological Society, it does get sustained by donation, so there's a donation basket there on the back table in case you still have a chance to make a contribution. We would appreciate that. And it's cash only because of, well, it's complicated, but that's the way it works. So this is our last public presentation talk until next fall, when on September 14th, currently scheduled though, we're going to have Daryl Cowan come and talk about terrains moving around, including, this will be on September 14th, Daryl Cowan, history of how an island in Alaska was next to Vancouver Island. But and there may be more to that talk than that, but that'll be a key part of it. But there will be field trips, at least one, maybe more than, probably more than that. Pretty surely more than that. We just don't have all the details quite figured out yet. So the thing to do if you want to go on a geology field trip through Quimper Geological Society is pay attention to the website and the announcements that come out in the emails, because once they're announced, it's first come, first serve, okay? So going into spring, summer, we'll have a field trip or two. We just don't have the details yet to announce them. So if you're interested, please pay attention. And speaking of the emails, we're trying to get the proofreading done more ahead of time and get those fixed so you won't quite get so many announcements any more than are necessary to cut down on any, on their number of emails. So apologies for that. And which brings us to Ralph Haugerud here. By the way, my name is Ralph also, and I'm also a geologist, but and I went to Western, and I went to University of Washington, but even though he may be younger than me, I haven't even checked on that, he preceded me through these institutions, Ralph did, and eventually he got into, including for his, at least at the University of Washington, his graduate work, doing geology and research partly on the basis of mapping in the North Cascades, and at some point afterwards he was hired by the US Geological Survey and got involved along with others, including the leadership of Roland Tabor, the late Roland Tabor, in mapping the North Cascades, and Ralph was there long enough to see it through towards the end, to get that geologic map of all the North Cascades put together and published. He also wrote weren't you and Roland co-author on that book, Geology of the North Cascades? Yes. Some of you may have that book, Geology of the North Cascades. I know at least one person does in here. And then speaking of mapping, along with the other research that is partly based on and derived from the mapping, he was around when lidar became established as a way of more precisely measuring the shape and details of the Earth's surface, and he got into that starting in the 90s, I guess. And so a lot of what he's talking about, what Ralph will be talking about today, is based on lidar data to show that much better details than previous maps do of the shape of the Earth. And what he's going to talk about, as I think you know, is trying to figure out, including from the lidar and so on, how that giant glacier that covered this area died. So without any further ado, here's Ralph Haugerud.
So, as Ralph mentioned, and as you all already know, this area was covered by a large ice sheet 15,000 years ago.
Can you guys hear back there?
And I want to ask how it died. And for context, it's worth pointing out it's been almost 50 years since John Mercer pointed out that our addiction to fossil fuel is filling the atmosphere with more CO2 than it's happy with. And we're on the verge of drowning ourselves by destabilizing the West Antarctic ice sheet. And since then, there's been lots in the popular press. It's been hard to find headlines like this, or this, or this, and a lot of focus, both popular and scientific, on how ice sheets might die. And there are various ways we can investigate that question. We can mount expeditions to the polar regions. We can use remote sensing. We can do a lot of things that cost a lot of money and get uncertain results. We can go back to the library and look up the physics of glaciers and calculate from first principles how glaciers must work and how they would die. Or, given that we are geologists, we can go to the past and see what has happened before. And I want to take advantage of the glaciers in our backyard and do that. So we are here, and there's a little star for Port Townsend on all the slides that show a map that has Port Townsend on it. And we are at the southwest corner of the Cordilleran ice sheet, which was part of the combined Cordilleran-Laurentide ice sheet that covered northern North America 1825, 15,000 years ago. And here in our part of the world, the ice sheet was divided up into several lobes, funneled between the mountains out to the sea, or between the mountains out on the Columbia Plateau. Wanda Fuca lobe, Puget lobe, Okanagan lobe, and to the east, the Columbia River lobe, Colville lobe, Purcell Trench lobe, and so on. And I want to look at these, and ask, how did the ice sheet die? And I think we get different answers for different places. And I want to step across the landscape and look at the possibilities. East of the Cascades, climate change, I think, is directly responsible. Glaciers are fed by big ice makers someplace up higher to the north, flow south. You turn the ice maker down, the glacier goes away. The Wanda Fuca lobe has the most complicated story, and I'll spend the most time talking about it and say things that I'm the least sure of. So, bring out your salt shakers. But the Wanda Fuca lobe, I think, is an example of a marine-based ice sheet that became physically unstable and floated away as sea level was rising. If you admit that, it's easy to explain how the Puget lobe died. It was fed from the east end of the Wanda Fuca lobe, and when that was gone, there was no more ice to flow south into the Puget lowland. I was going to show you an animation here, but it doesn't play on a Mac, so we're not going to do it. We're going to talk about it. When we speak of glaciers moving, and they move in two senses. One is that they advance. The front edge moves out ahead of, they retreat, the front edge moves backward. But during all of this time, typical glacier is also moving internally, sliding over its bed at speeds greater than the advance of the front of the ice sheet, or greater than the retreat of the ice sheet. Glaciers can also just stop moving and melt. We think that's a little less common. The clear sign that the glacier is moving and moving faster than its margin is the moving ice carries debris, and the debris melts out and piles up at the edge. And if the edge is stationary, we can see this piled debris, and that's a sign that the stationary edge of the ice sheet was backed up by an ice sheet that was moving internally, sliding over its base, deforming internally and carrying rock with it. It's dumped out to the edge. So a glacier is a place where snow accumulates, turns to ice, which flows, slides downhill, and melts. At higher elevations, it's colder, snowfall exceeds melting. At lower elevations, it's warmer, melting exceeds snowfall. Someplace in between, there's an equilibrium line altitude, where the accumulation of snow is balanced by melting. And it's the point where the glacier turns from its accumulation zone to its ablation zone, and is a nice way to understand some glacier physics. Ice is plastic and flows, as I said, and it flows if you put enough stress on it. And the glacier movement reflects a dynamic balance. On one side, we have the force of gravity, the loss of gravitational potential that is dissipated, that makes the ice move downhill. The other side are the dissipation processes. The resistance to internal deformation, the friction inside the ice sheet, and the friction at the base of the ice sheet. And if you, for example, lose the friction at the base of the ice sheet, then glacier flows faster, and you dissipate more energy with resistance to internal deformation until you lose gravitational potential. So glacier is a balance, and if you change part of the balance, some other part has to change also. I'm having a hard time between make a red spot and go forward. Glaciers are heavy, and when an ice mass forms, it weights down the crust of the earth, and the crust sinks into the mantle. And the physics are very nicely exemplified here. And we can be a little more formal about it, make a cross section. And we have here kids on an air mattress above a swimming pool. And the mass of the ice forces the air mattress down into the pool until you pushed away enough dense water to counterbalance the mass of the glacier. And this process is called isostasy, from the Greek, equal standstill. And some things happen as part of that. One is if you push this down, this area has to tilt, and if there's any strength in this air mattress at all, you often get a little bulge out here where the air mattress is lifted above the water. Out here, a bulge. And if you melt the glacier, the bulge collapses, this part rises up, and it untilts. And also, the water in the glacier is added to the world ocean, and sea level rises everywhere. Sometimes this rises faster than sea level does, and so, for example, around here, as the glaciers melted, sea level fell locally. The world oceans were filling up, but the area underneath the glacier was rising even faster than the ocean was filling, and so sea level dropped quite dramatically. Sea level. This is a depiction of some of the data we have for the history of sea level over the last 32,000 years to present. And at 25,000 years ago, sea level was maybe 120 meters lower than it is at present on average around the world. And that's because that's the time of maximum ice accumulation throughout the world during the last ice age. Our local ice age was out of sync with that. Ice began growing here in a big way, maybe 20,000 years ago, and lasted till about 12,000 years ago. Which means that throughout the time we were growing ice in the southwestern part of the Cordilleran ice sheet, world sea level was rising. So the world as a whole was thawing. And don't ask me to explain the climate that allows that to happen, but that is what happened. And it makes for interesting sea level histories here. I'd like to talk a little bit about how geologists do time. And for many of you this is obvious, and I apologize for belaboring. We do time primarily by superposition and by cross-cutting relationships. We can go to the south side of Discovery Park in Seattle and look at these layers stacked up here and say this is the bottom of the hill, it's the oldest. On top of it are these layers, on top of it are these layers. We can see a landscape with shallow streams, shallow lakes and streams, overlain by a deeper lake that had icebergs floating in it that made drop stones, overlain by a stream delta that was very sandy. And then cutting across all of this is a landslide that's younger still. And so it's pretty straightforward to number them in their age. And that's the most robust measurement of age we have, is that superposition and cross-cutting relationships. We also, for lots of reasons, want to talk about how old things were, numerical ages. And those are a little more complicated and a lot less certain. But for glacial deposits, the big thing is radiocarbon. It's the appropriate technique for things of this age. And radiocarbon is based upon the observation that cosmic rays turn nitrogen in the atmosphere into carbon-14, which is unstable and slowly decays to carbon-12. And you can capture, and if you assume that the cosmic rays hit the atmosphere at a constant rate, then you can take a box of atmosphere captured sometime in the past and measure how much carbon-14 is left relative to carbon-12 and figure out how long that box has been closed. Now, cosmic rays have not been hitting the atmosphere at a constant rate. It's not quite that simple, but we have lots of samples of the atmosphere from the past that we can get approximate ages for by other means, and we can calibrate the cosmic ray production of carbon and know what the atmosphere looked like 2,000 or 12,000 or 20,000 years ago. 200,000 years ago, the carbon-14 is all gone, we can't do it. But with a lot of work by a lot of people over a long period of time, we can calibrate carbon-14 ages and know pretty well what they mean. And I will mostly speak of calibrated ages in this talk. Unfortunately, not all samples of carbon from the past are pieces of the atmosphere put in a box. And we have good samples and not so good samples. Good samples are materials that have collected their carbon from the atmosphere directly. And these can be bones of deer that ate plants that captured carbon from the atmosphere. They can be leaves of those plants, they can be wood. Not so good samples are things that have collected carbon not from the atmosphere. And the big problem children are marine shells that are sampling ocean water and ooze out of freshwater ponds, gitcha, or pond scum. And there are well-documented, marine samples, it's pretty systematic. If you can go to the museum and collect shells that were taken off the beach before nuclear weapons testing screwed everything up. In the northeastern Pacific, they're typically 700 years too old. Pond scum is a little more problematic, but it's clear in many cases that we get pond scum ages that are too old. And so one of the things that I'm going to do that a few of you will recognize in this talk, others you won't, is I'm going to ignore a lot of published radiocarbon ages because they're from shells and pond scum. So, now with that as background, how did the Cordilleran ice sheet die? And I'm going to start east of the Cascades, where I actually know the least, but I think the story is the simplest. And we're going to look at evidence for the ice machine slowing down. And for amusement, this is the Withrow Moraine on the Waterville Plateau, northeast of Wenatchee. This is the Columbia River Valley coming through here. Brewster is right about here. This is the Okanagan Valley down which the ice came and flowed out across the Columbia Plateau. Looking at a map view of this, we were just looking from here to the northwest of the Okanagan Valley. East of the Cascades, there are several lobes of the ice sheet. The Okanagan lobe, the Columbia River lobe, Purcell Trench lobe, and a few that are small whose names don't fit on this slide. Over the last year or so, I've been working with lidar data to try to make a map of where the ice got to, the maximum extent of the ice east of the Cascades. And this is work that's still in progress, it's incomplete. It's worth talking about because it's based on new topographic data we haven't had, so I'm getting better answers than we had before. And I'm not trying to get the whole story, but just reconnaissance, where did the ice get to? And you may be able to see on this some very short green lines here, many places. These are indications of an ice margin, places where the ice has piled up little ridges of debris. When the ice margin was standing still for a short period of time as it retreated. These brown dots are haystack rocks, which are big chunks of basalt ripped up off the edge of the plateau and carried south and dropped by the ice sheet. They're a clear indication the ice got to that point, if not further. And the yellow line here is what I've figured out so far about where the ice got to. These yellow lines are wrapping around peaks that stuck up through the ice sheet. One of the things that was quite striking as I did this, and I'm going to change some colors here, and I've turned the green lines to red ones, and I've turned some of them blue, is that these indications of where the ice was as it retreated, the ice margins, the moraines built by retreating ice, are at many elevations in many places. And to illustrate that, I've taken all of these pieces of red in here. Each one I've asked what's its average elevation and how far north is it. And I'm going to show you a graph that's height, sea level versus northing. It's this one. And again, this is the south, which is the bottom of the picture. This is the north, top of the picture. Elevation in meters going from, well, that's lower than Wenatchee, to up to 7,000 feet. And these moraines, these recessional terminal moraines, are at many elevations spread across the landscape. We can look at just a little clump of them up in here, and they span 1,500 meters of elevation. We can look in close. We're down about 1,000 meters here. This is high ground, low ground, the color change. These are ice marginal drainage channels where water's flowing along the edge of the ice and carving out a shelf on the hillside. And on some of these channels, you can see the little ridges that bound them, or in here. This is an indication of ice whose margin is at least temporarily standing still while the ice is moving inside and delivering debris to the ice margin. So the ice sheet, as it's stepping, edge is going northward and downhill, is lowering down, melting out. The ice is still moving, it's still alive. Same thing here. This is a higher ridge, and the ice was wrapping around it, and here are the morainal ridges built by that ice wrapping on higher elevation ridge. So the ice is live, it's still flowing when it's up at 1,700 meters, when it's down at 1,000 meters, when it's lower, at this location right here. You see the same story to the south on the Okanagan, on the Waterville Plateau. where these are two depictions of terminal moraines that show up on your photos, and this is what I've mapped. This is what Dory Covenant and Olaf Sledmaker mapped. They're quite similar. We looked at the same air photos, saw the same features, they're real. And they're recording ice that's got as far south as here, and then the margin backed up while the ice conveyor belt internally was still moving, still delivering debris. So, these are reconnaissance observations, but they show pretty clearly that this is a case where climate change happened. The ice maker slowed down, and the glacier slowly retreated. And this is what I think of as a normal glacier death. It's what I learned about as an undergraduate. We go west of the Cascades, the story's more complicated. We have some abnormal glacier deaths. So let's step west of the Cascades. We were just looking at the Okanagan lobe and step up in here. And parts of the story are common to both the Puget lobe and the Wanda Fuca lobe, and I want to review the basic setting to start with. Maximum ice extent was at about 15,400 years ago. And this is Fraser glaciation, the last advance of the ice sheet. And we divide Fraser glaciation, this is a time diagram, old to young, into three stages. An early Evans Creek stage, which is known from Mount Rainier and from outside of Vancouver, where little glaciers formed in the mountains and flowed down the valleys. And I'm not going to talk about that anymore. Evans Creek ice reached its maximum maybe 24,000 years ago. This was followed by the Vashon stage, where ice collected in the coast mountains of BC and flowed south in the Puget lobe and up to Wanda Fuca. This is the major glaciation of the Fraser episode, and occurred between maybe 19 and 15,000 years ago. And ice flow again was out of the coast mountains of BC, out of actually the state of Georgia filled with ice and probably had an ice surface elevation there of 6,000 feet, high enough that it was an ice source itself. And as ice growth continued, the ice got high enough to flow directly over the Vancouver Island ranges out to the Pacific. And late in the Vashon stage, we know ice came down the Skagit River, but not early in the Vashon cycle. Derek Booth did his PhD on this and came to the conclusion that the equilibrium line altitude for the Vashon stage of the Cordilleran ice sheet was about 1,250 meters, which puts it basically over the southern San Juan Islands. And to me, that's significant because it says the Wanda Fuca lobe here, and the Puget lobe, were fed through the same pipe. That you can't adjust the end of the Puget lobe by turning the ice maker up or down here without affecting the Wanda Fuca lobe at the same time, and vice versa. That any source signal in the climate, that is, what's happening in the coast mountains, anything you want to appeal to there to change the position of the end of this ice sheet or this one has to affect the other one as well. That's what I just said. And then there's a younger Sumas phase, that's ice coming out of the Harrison Lake Valley and flowing down the Fraser lobe. The abstract that's online, the one that I gave Ralph many months ago, I said I'd talk about the Sumas state. Then I put the talk together and realized that I wouldn't get you guys home in time for dinner if I did that. So if you really want to know, ask me afterwards. There's been a lot of work done on the Puget lobe, especially in the Vashon age, and I especially want to point out what Robert Thorson taught us many years ago. The first good work in the Puget lobe was done by J. Harlan Bretz for his PhD research at the University of Chicago. He did the work while he was teaching high school in Tacoma. And he recognized that as the ice sheet retreated, it opened up the southern lowland, and a large lake formed. It was dammed by the ice at the north, and the lake drained to the south and out the Chehalis to the Pacific Ocean. And he called this lake Lake Bretz, for one of the first geologists who studied this area back in the 1880s. And Bretz named this sorry, not Lake Bretz, Lake Russell, for Israel Russell. And this was in 1912 when Bretz did that. 60 years later, 70 years later, Thorson recognized that as the ice retreated further, it opened up a new spillway where we are. And Lake Russell dropped dramatically. Water ran out over the Quimper Peninsula in the east side of Wanda Fuca and formed a lower elevation lake, some 60 meters lower than Lake Russell. And Thorson called this one Lake Bretz. And I think that's the next slide here. the thing for our story that's important here is the existence of Lake Bretz, the fact that the water could run out this way, shows that while there was still ice over Admiralty Inlet to dam Lake Bretz, there was not a bounded glacier in the state of Wanda Fuca, because there was a place for the water to go to. And if there had been healthy glacier out in here, we wouldn't have formed Lake Bretz. Drainage would have continued to be out through the Black Lake spillway, and we'd see a longer lived Lake Russell. I had myself. Thorson also recognized and described in some detail a large number of deltas built out into these lakes. And the deltas are easy to find. They're the sand and gravel pits that have made our skyscrapers and freeways and everything around here. And he surveyed the elevations of the delta tops to define the lake levels and found they're tilted. And a fairly uniform pattern for both Lake Russell and Lake Bretz, and for that matter for the marine limit after Lake Bretz drained, showing that after that time, the landscape has been tilted up about 1 meter per kilometer. This is the tilting of the air mattress, the edge of where the kids were. The glacier to the north is the weight. It pushed the crust down more under Vancouver than under Olympia. And as a result, Western Washington got tilted down to the north by about 1 meter per kilometer. We build deltas into these lakes. Ice goes away, everything pops up, and those deltas define plains that are now rise 1 meter to the kilometer up to the north. So yes, we've got tilt. Now, on to the Wanda Fuca lobe, which was actually first described in any detail at all by J. Harlan Bretz. And I'm going to tell you a complicated story, and I apologize for how complicated it is, but it's also part of why it's so fascinating. And I'm going to try to step through in some sequence here and give you the pieces of the story. But we're going to go from out by Lake Ozette to off of Mia Bay, the entire state of Wanda Fuca, to the Eastern Straits, off to a core that was collected in 2002 on the continental slope west of Vancouver Island. And I want to make several points. The first is that for 50 years we've had the age of the Wanda Fuca lobe wrong. It's younger than we thought it was. And let's go there. This is work by Cal Heusser, who was interested in he actually collected samples for pollen analysis to find out what kind of forest grew after the ice sheet left. And that was his interest here. But he found samples he could date from the recessional sequence after the Wanda Fuca lobe was here, and published an age of 14,460 radiocarbon years from the bottom of a bog just northeast of Lake Ozette, which sits over in here. And if we calibrate that age, given what we now know about the history of the atmospheric carbon reservoir, that's 17,610 years ago. And we've known for 50 years that bog filling is younger than the ice sheet. I mean, the bog is younger than the age as he got out of that bog bottom. And he understood there was a problem there. His explanation was that, well, these trees were growing on ablation moraine that has melted out debris on dead ice after the glacier was gone, and left behind piles of ice with dirt on top that the forest could grow on. And when the ice finally melted, the forest and the soil collapsed in a jumble and made till, ablation moraine. And so that's how you can have these big logs, these thick sections of till, that are younger than the glacier. And that was a perfectly good explanation until we got lidar topography. And he didn't report precisely his locations. He reported them to the nearest quarter section. We can plot those on a map and look at them close up here. And he was almost certainly in this road cut along and through here. Or in this case, in this road cut here or over here. Or in these road cuts in here. And in every case, these road cuts are into a surface that's very nicely fluted. That's the soul of the ice sheet. This is not ablation moraine, a jumble made by dead ice. This is lodgement till made by ice flowing over the landscape. And his samples were of a forest that was overridden by the glacier. And so I think it's pretty clear that, say, these are lodgement till, not ablation moraine. And the maximum age, the maximum extent of the Wanda Fuca lobe is younger than these ages here, which is, well, younger than maybe 15.7 or so as an average. And it's got to be, so maximum extent was 15.5 or maybe younger than that. And this age here must be a problem. That we sampled a bog that happened to have dead carbon in it, that not all of that pond scum, the ooze in the bottom of the pond, was made by carbon captured from the atmosphere. So, Wanda Fuca lobe is younger than we thought. Then we can go offshore and look at some work, again, done 40 years ago, and see that the Wanda Fuca lobe was grounded, and we know from other work that it later probably floated. So here, this is basically bathymetry, showing a very complex irregular bottom that looks like the tunnel valleys of the Puget lowland, that show that the Wanda Fuca lobe was grounded. Hertzer and Bernhold also had the benefit of grab samples and some coring they did, and that confirmed to them also that the Wanda Fuca lobe rode on its base. It was not an ice shelf floating. We can also look at this and see that at some point the Wanda Fuca lobe reached out to the edge of the continental shelf. And I'm not going to show you the picture here, the data, but we'll get to it later. There's good evidence indicating at some point in its history the Wanda Fuca lobe then floats. So it's a transition in it. Now, I'm not sure I can explain why I think it's important, but if we look at a longitudinal section of the State of Wanda Fuca, I think it's likely that at the time of ice maximum, the floor of the Wanda Fuca lobe sloped down to the east towards the source of the ice. This is bathymetry. I've taken samples of bathymetry inside the yellow box, basically at every pixel in this raster, and projected those samples onto the line down the middle of the box. And I'm looking at those data here. So this is from east to west, sea level, deep, and the stronger the color and the bluer the color, the more samples at the bottom there are in that bin. And this is showing us that we have a floor of the State of Wanda Fuca that gets gradually deeper out to the west. And we get up to the continental shelf, and it jumps up and it's flat. Not too surprised. That's modern sea level. We can also look at relic shorelines out by Sand Point, Lake Ozette, and here in Port Townsend, and know that there was at least 0.3 meters per kilometer down to the east tilt at Wanda Fuca lobe time. That's a minimum. It could easily be more than that. I can't show that. Here's what happens if you put a ½ meter per kilometer down to the east tilt on the bathymetry. It makes the bottom flat. We're seeing constant depth. If you put a meter per kilometer, it makes it deeper landwards. And this is the magnitude we're seeing in the north-south section through the Puget lowland. And I think it's plausible for this east-west section outside of Wanda Fuca. This is the piece that I think we know best and is most telling. At some point in the history of deglaciation, there's a dramatic change in ice flow direction in the eastern side of Wanda Fuca. And this is primarily from lidar topography, a little bit of library work also. If we go to Whidbey Island, Oak Harbor is right over in here, you can see the north-south flutes here, produced by Vashon ice flowing from Vancouver to Olympia. That's main face flow. That's the pattern that dominates most of the Puget lowland. And on top of that are these from the northeast to the southwest flutes that are younger. Overprinting relationships give you the time sequence. And then the ice is gone and sea level is higher, and this has all been smoothed by wave action and sea level fell as the land popped up out of the water because of glacial motor. If we go to southern Whidbey Island, and Holmes Harbor is over here, Langley's to the north, is it Freeland is to the south? You can again barely see the north-south flutes here of main Vashon ice flow, and then see these flutes flowing to the northwest through here. And you may get your eye caught by this sort of spider web, the irregular things, that I believe are crevasse fillings that are at approximately right angles to the flow direction as you would expect.
Yes.
We can go west of here to Squim. Squim is up in here. And see that at higher elevations, you can see flow into the Olympics where the ice then melted. And younger than that, cross-cutting, at lower elevations only, is flow out to the west alongside Wanda Fuca. We can go to the library, where Ali and Chapman worked on Vancouver Island in the 70s, They reported that main flow was over the Vancouver Island ranges in the state of Wanda Fuca, and there was later flow along the shoreline, along the state of Wanda Fuca. Put these all on a map and had a few more observations on Lopez Island and the lower Skagit Valley, and you can see the main face flow pattern that's really obvious in topography, and we'll see more of. And then overprinting that, flow outside of Wanda Fuca, flow reorganization. So I can put together, hypothesize a sequence of ice history with maximum extent at about 15,500 years ago, where at Port Townsend, ice is flowing from the north to the south, hits here and goes out that way. Something happens, and flow reorganizes itself, and the Wanda Fuca lobe basically goes away and makes a big hole, and ice flows into that hole. The ice retreats further, and at that point, we need an ice dam in Admiralty Inlet to dam Lake Bretts, which then flows out down Beaver Valley and Discovery Bay, where we know there had to be either open water or an ice shelf. And then ice retreats further still. Admiralty Inlet opens up. Puget Sound becomes salt. It's no longer a lake. And there is a nice little bit of terminal moraine at Coopville. We can see the Cane Kettle Complex at Partridge Point. There's moraine in the bathymetry. Here, Smith Island is an ornament on that moraine. We pick it up again at Cattle Point, and then we go to the Colwood Delta, west of Victoria, that requires ice in here to force water to flow through this way. So the Coopville moraine records a stabilization of the ice margin for some period of time there. A further retreat, there's a recessional moraine at the mouth of Rosarian Strait, and then further retreat, and the system's ice-free. And this has happened by 14,500 years ago, because Dory Covenant got a wood age out of a bog up the middle fork of the Nooksack, about that age some time ago, which shows that the ice is gone. So, in less than 1,000 years, or 1,000 years max, ice has retreated from the edge of the continental shelf to border probably, or if not further. Now here's the part that I can't explain well. If you want more details, quiz me afterwards. I start the slides and we can go through them. But if we go out to the continental slope west of Vancouver Island, there was a core collected that I think shows that this all happened in 2 centuries or less. And this is the Marion Dufresne. It was a French research vessel that was chartered to I'm not sure whom, but did a cruise out here at the time. And they very carefully selected a site here that's off the continental shelf, so it's deeper and below wave base throughout the entire Pleistocene. It was on a small hill, so it wasn't scoured by turbidites. That's far enough away from, say, Wanda Fuca to not be immersed in glacial marine sedimentation. It was a very carefully selected site, designed to give, if possible, a continuous record through the late Pleistocene of what's happening out here. And that's a really big advantage. The big disadvantage of this core is you know how old things are because you date the shells you find in the core. And those shells are sampling marine water, and you don't know how old the water is. So these are 2 side-by-side depictions of what was found in the core. And unfortunately, it's not labeled in depth below the seafloor. It's labeled in age, which corresponds to depth, but it corresponds to ways that are maybe unknowable. And on the right is how rapidly the core accumulated. Actually, how rapidly the stony part, so we leave out the organic ooze. And this is a logarithmic scale. So if we step this way, things are accumulating much faster. On the left is a measure of how much fine sand or coarser debris. This is 250 microns or 1/4 millimeter. If grains are that big, they need ice to get them to this site, that they won't float in the water to get out there. They're not pelagic sedimentation. There's something that's being carried by ice rafts. So ice rafted debris, IRD, how concentrated it is. There's a pulse here, and a pulse here, and then another pulse here. And the history of this core, as seen by the people who worked on it, Tim Cosma and Ingrid Hendy, first is that there's an early ice rafted debris event, maybe 46,000, 45,000 years ago, that's older than Fraser glaciation. They see an uptick in sedimentation rate at about 30,000 a little before years ago, and they see this as the beginning of ice growing in the mountains nearby. This is the onset of the last glacial cycle, Fraser glaciation, in this part of the world. They see an ice-rafted debris event here, and I think I screwed up my slides here. Oh, I did. They call C2, and the interpretation of the C2 has two parts is mine, not theirs. But I think we need to see a history that has the Wanda Fuca lobe first being on the shelf and perhaps not shedding icebergs because it's grounded, and it may be grounded in shallow water or even on dry land because global sea level is low at this point. And then it reaches the shelf margin and sheds icebergs. And then at some point it goes away. And so I think we're seeing the onset of C2 is where the grounded Wanda Fuca lobe reaches the shelf margin and begins shedding icebergs. And this, from the ages near Rosette, we know has to be after 15,500 years ago, or no earlier than that. And then we see a very high intensity pulse, a late C2 pulse, that I think is the Wanda Fuca lobe floating, breaking up, and going away. So lots and lots and lots of icebergs. And then after that, there's another ice-rafted debris pulse, which Cosma and Hendy interpreted as being ice emptying out of the Georgia Strait. So we've taken the 1,000-year window for the Wanda Fuca lobe to go away and collapsed it quite a bit because we can date this red bar here, and through arguments I will not go through, I think that's no more than 210 years. And that's the ice march retreating from here to here.
In 210?
Yeah, or less. So, why did it do this? And there are lots of reasons that have been proposed, and they all make sense, just some I think make more sense than others. I don't think it's the ice machine working less well. It's not regional warming or drying, because this is happening before the Puget lobe retreats, because the Wanda Fuca lobe is gone by the time the Puget lobe is halfway gone. So it's not the source area making less ice. You can rule that out. Ingrid Hendy, who did the work on the core, has pointed out that if you look at the fossils and look at the isotopes in the core, there's a couple of degrees Celsius warming of surface waters in this time period. And she thinks it's likely that the warm ocean water has melted the ice sheet. I think at the beginning of this episode, the ice sheet's grounded, and if you can't get water underneath the ice sheet, it's hard to efficiently transfer that heat to the ice and cause it to melt. So I don't like that idea. I'm going to rule out both of those. And I think it's more likely that rising sea level triggered a floating feedback, a positive feedback cycle. The collapse likely coincided with the transition from grounded to floating. We see that in the geologic record. We know the world ocean volume was increasing at this time. We know we've been loading the crust by the growing ice sheet, causing things to sink. And so locally, relative sea level is rising as well by isostatic compensation. And we know that much of the Wanda Fuca lobe floor probably sloped down to the east, which makes this feedback loop work better. That if you have a grounded ice sheet and float a little bit of it, you lose basal friction. So the ice sheet deforms internally and spreads. And as it spreads, it makes it steeper and further upstream, which causes it to spread some more and thin some more and spread some more. There's a positive feedback that works really well if the base is landward sloping. And I think that's what likely happened here. And when people tell you the West Antarctic ice sheet may just collapse and go away, well, yeah, it did. Something like that happened here. So perhaps the Wanda Fuca lobe died because rising sea level floated it away. Now, on to the last one, the Puget lobe. And if you grant me the Wanda Fuca lobe collapsed rapidly before the Puget lobe went away, this is easy. I think it's a supply chain problem. And the Puget lobe is remarkable for two things. One is this beautiful preservation of the soul of the ice sheet. We'll look at a picture here in a minute. And the other is that we don't see nested end moraines like we do over in the Okanagan lobe or the Columbia River lobe, what they call east of the Cascades. This is just west of Tacoma, and you can see that the flutes here, they're spectacular. And most of the Puget lobe looks like this. There's messy stuff in a few of the lower areas where perhaps in the tail end of glaciation as the ice was melting, there was debris deposited on the surface, then it got dropped in a jumble, like Haugerud thought happened out by Rosette. But mostly the Puget lowland looks like this, a spectacularly preserved base of the ice sheet. And I think part of that preservation is that there are no end moraines built on top of it to mess things up. There are very, very few end moraines in Puget lowland. There are scraps south and west of Olympia, amidst the outwash flats. Most of these moraines, which must have been there, got washed away by the meltwater coming off the ice sheet. There's a little bit of moraine on land at Coupeville, and I mentioned the segments that are submarine to the northwest of there. Rosario Strait moraine make up the Coupeville moraine in aggregate. There's submerged end moraine here. And then there are lots of younger Sumas phase end moraines in the Bellingham area. But the absence of end moraines through here is really, really quite striking. And I think the reason for that, well, I'm getting ahead of myself. We can look at the ages here, and this is a map showing the extent of the Puget lobe at Port Townsend. The X's are a selected subset. I'm parsing the data very strongly here. Published radiocarbon ages. Mostly I've ignored lots and lots of shell ages and a few pond scum ages. And I'm going to plot them on a north-south graph, north to south. And on that graph, I'm going to have as a zero line for the distance north-south, the contour on the glacier surface that went through the University of Washington. So here is north, here's the south, here at zero is the University of Washington contour, Coupeville, Olympia, maximum ice extent, and the border is up about here. And these blobs are age probabilities. Each funny dish-shaped thing is a sample, and we have a measurement error on that sample, and we also have a calibration error as we adjust for the composition of the atmospheric reservoir. And those two combine to make a fairly uneven distribution of possible ages for that sample. In any given one of these, this where it's wide is the most likely age, but it could be as little as much as this or as little as this. And any interpretation has to allow for the possibility that the true age is here, but it's most likely up in here. I think it's this sample right in here, and that's one of these, is the one during Covenant collected east of Bellingham that shows that the system was ice-free at 14,500 years ago. And from these we can jump ahead. These are all samples from beds that were deposited before the glacier arrived. We know that from the outcrop. They're collected from underneath the till. These are all samples after the glacier left, collected from on top of the till. And so this period of time from here to here, at this place, is when the glacier was when the glacier was here. And this, back up here, this solid gray line is my interpretation of the most plausible history of southward advance of the ice sheet, which reached its maximum about 15,400 years ago south of Olympia, and then retreated rapidly to the Coupeville moraine, where it may have stood still for a while, and then retreated more slowly north. And we don't know how rapidly, because these are bog ages, pond scum ages, and not sure what to think about them. These are shell ages. Basically, there's no constraint as to where the curve is in here. What we know is we've got to get from here to here, stand still, and then be gone by this time. I think Puget lobe retreat was fairly rapid. Might have been as little as a few centuries, maybe as little as several decades. And how'd that happen? Well, again, let's go to our flow reorganization in the northern Puget lowland. Puget lobe was fed by ice flowing over the San Juan Islands and south. At some point, that ice starts flowing to the west into the hole left by the collapsing Wanda Fuca lobe. And if we draw a very simple idealized cross-section through here, south to the ice margin, very, very idealized. Here's Coupeville. Here's the north where the ice comes from. It flows down this slope to Olympia. At the very edge, it gets thin enough it doesn't flow anymore. And when it is flowing, at some stage, we build a moraine here. And then we start sucking ice out of this area. And that drops the surface slope of that area. We probably reverse the slope in here. And this gets thinner. We get a larger extent when the ice is too thin to flow. It can't build a terminal moraine there. That continues until the Puget lobe is gone and the ice is stabilized again at the Cookeville moraine. Something like this, I think, is required to explain the absence of end moraines and the beautiful preservation of the soul of the ice sheet in Puget lowland. Again, not that the ice machine broke. It's a supply chain problem. The ice is not getting here anymore. So how did the Cordilleran ice sheet die? And the answer is in different ways in different places. East of the Cascades, the climate machine changed. The ice machine slowed down. The Wanda Fuca lobe, there need not have been any change in climate at the time it went away. There may have been change in climate, we don't know. But I think the proximal cause is the rising sea level floated it away. With the Puget lobe, and this is where I began, this is looking at the Puget lobe, the issue is the supply chain broke down. The ships that carried the ice weren't making it south of the San Juan Islands anymore. A few references. If you'd like to explore this story, go to the Washington LIDAR portal and just look around. It's fascinating. You can waste days doing so. It's very, very entertaining. And I hope you will agree that it supports much of what I've said. Much of the story has been published in GSA special paper chapter that is available for free online. It's not locked up. You can get it. Ingrid Handy and I wrote an abstract on the Wanda Fuca lobe some years ago. I did a map of the Kitsap Peninsula that describes some features, and the Bellingham story that I didn't talk about is in this report. Sorry. In this report by Dory Cutler and myself and Don Easterbrook. Anyway, thank you. Oh, which Ralph are you whispering at?
So we will, if you have a question, I will bring you the microphone so everyone, if you have a, is this on?
Yes.
If you have a question, I'll bring you a microphone so that everyone can hear the question, so that Ralph doesn't have to repeat it and can just answer it. So who has a question?
What do you need to firm up your interpretation of the Wanda Fuca? What do you need more in the way of data?
Are steep and rocky and wave washed. And I've spent a lot of time looking at the LIDAR alongside Wanda Fuca and have yet to see much of anything that says anything diagnostic. I think there's a real preservation of the record problem out there. The two things that I would most like to see, one is a record of where the lake glacial shoreline was on the continental shelf. And I don't know how you would get that. Maybe you could do it with a combination of shallow seismic reflection and coring. Maybe you couldn't. But if you could somehow find out where the shoreline was at 14 or 12 or 15,000 years ago, that'd be really nice. The other thing that you could do, I think, that would help reinforce this story is find out how long Lake Russell and Lake Bretts existed. The Washington Geological Survey employees who mapped in the South Sound, Tim Walsh, my names are failing me now. Zahan, Mike Polans, and others who looked there, Josh Logan, said that where they found shoreline outcrops of varb sediments deposited in those lakes, they never saw more than about 20 barbs. And this is what I've seen kayaking in the South Sound also. And the real problem is that where you see those sediments are on steep slopes, which means the top slopes are also steep, and the top of the section is not preserved. You don't know what's there. So and the barbs are fairly thick in some places, and my guess is they get thicker to the east as you get closer to the Nisqually, which is the major drainage channel coming into those lakes. And I think what you want to do is go out and map barb thicknesses to get a thickness pattern, to figure out where the section is going to be thin enough you could actually afford to core through it. And then go looking for upland basins, things that would have gone dry when the lake's emptied, but were below lake level when they were there, and that are flat, so there's no problem with the top of the section being eroded away, and core them. And you could count barbs and figure out how long those lakes lasted. And my suspicion is you're going to get numbers that are well less than a century. And that would help substantiate this story. That wouldn't prove the Wanda Fuca lobe collapsed by floating fitting feedback.
And Ralph, maybe you have to repeat the question because the recording will only record your microphone, I think. Is that right, Wesley?
Yeah, I was just curious. All of the ages that you referred to were carbon 14 ages. I'm curious if there were any useful volcanic ash layers that occurred during a period of time that would help with any of that dating.
Yes, there are. The question is, are there volcanic ash layers would help with the dating? And the answer is yes. But unfortunately, it gets more complicated than that very quickly. And I don't know the volcanic ash story as well as I should. I apologize for that. But for example, the Mount St. Helens S tephra are about, well, how old are they? And they're estimates that range from 13,000 to 16,000 years or more old. And those estimates, some of those are calibrated and some of those are uncalibrated carbon-14 years, and that doesn't help the discussion any. But Jim Beget and colleagues found Mount St. Helens S underneath Vashon Till in the Ohop Valley south of west of Mount Rainier, and published a paper in 1997 about this, where they said that the Mount St. Helens S is thought to be 13-some thousand years old, but it's underneath the 13,000 radiocarbon years, but it's underneath the Vashon Till, which we know is about 14.5 radiocarbon years. Therefore, those young ages for the ash are wrong. And I think at that time, what we thought was the maximum age in the Puget lobe is actually 1,500 years too old. And their discovery, if you take the younger ages of Mount St. Helens, is quite in keeping with the younger age for the Puget lobe and the Wanakee lobe. There are interlocking uncertainties here, and it's hard to unravel them all. But one of the things to do is find more tephra, and also go, tephras we do know about, get much better ages on them. And that isn't always easy.
Anybody else?
Ralph, when you're looking for topographic features on lidar, like the moraines, do you have to do that all just by an observation, or can you do that in GIS in sort of automated way?
I have not tried automating moraine detection. I have, over the years, spent time trying to automate the detection of things in LiDAR, and I've made a couple of serious attempts, and in each case I've decided that the time I spent trying to automate it would have been much better spent looking at pictures and drawing lines. But I am better at interpreting topography than I am at writing code to interpret topography. I'm not saying it's not doable, but I've not succeeded. But that is one problem. This is my ability to see things, and you're taking some faith that I was actually had enough coffee that morning, that I illuminated things in the correct direction, that I didn't forget and skip something, and having someone else repeat this wouldn't hurt.
If you said, I didn't catch it, but how long do you think that the ice was at its maximum position in the Puget, on the Puget lobe and the Wanakee lobe?
I think what we know of the ages involved suggests that there wasn't a still stand at the maximum. The ice got there, and then something else overtook it and it went away. That the ice was advancing.
So it
when all of a
just
sudden-
advanced and then it,
Yeah.
and then it either collapsed or melted back.
It collapsed, yeah, and then melted back because it lost its ice source in Puget lobe. I mean, that's because the timing seems so tight. And that's a different story than, say, the Okanagan lobe, which has this moderately substantial constructional moraine in its furthest extent. And it's a different story than the Sumas advances around Bellingham, some of which have quite substantial moraines. We can count, I forget how many Dorian I got. We got 9 phases of Sumas glaciation, at least 5 of which had well-developed end moraines.
On the north side of the Olympics, we do some hiking, and there at about, is it 35 or 3,800 feet, there's concentrations of granitic boulders that we cross. And I'd always thought it was lateral moraine, but after hearing this talk, I guess it was from the advance of the Wanda Fuca lobe to the south. But anyway, it's quite distinctive, at certain elevations along there. Not a real moraine, but certainly concentrations of erratic boulders.
Uh-huh. Yeah, I don't know much Olympics geology. It's a deficiency in my background, and I'm glad to hear there's what ought to be out there.
You started by saying the reason you do this is because the West Antarctic ice sheet of how fast it might go. But you never close that loop. So what's this tell you about how you think the West Antarctic ice sheet might disappear?
Yeah. Let me clarify. I do this because I enjoy looking at topography and solving puzzles.
You justify it.
And the West Antarctic provides a context for what I like to do, making sense to you guys, I hope. I think when people talk about collapse of ice sheets, we should take them seriously. There's one other part of this that I would love to tell you a story about, but I can't, so know that I'm waving my arms here trying to fly. I wouldn't be surprised to discover that we could maybe show that ice could not advance down the state of Wanda Fuca until the ice had directed enough meltwater that way in front of it to fill it in with sediment, that the ice would not advance over deep water. And clearly, by the time the ice had left, it had excavated all that sediment. If we go out to the bluffs on the edge of the state of Wanda Fuca, I would expect we'd find that the advanced outwash sediment is fluvial, not marine, and it records flow to the west, not fans off the Olympics going out to the north. And that ice does not advance over deep water very happily. And this is better substantiated in the Bellingham area where the Sumas re-advance. I don't know if it had to wait, but it didn't happen until there'd been enough isostatic rebound for the ice to advance over ground instead of over salt water. And you can suppose there's an hysteresis here where the advancing ice delivers sediment, builds a carpet it can travel over. And then the ice, while it's there, erodes that carpet, makes a deeper base, but the ice is thick enough, it stays grounded. And if you somehow float the ice sheet, it thins and retreats and cannot re-advance until you could turn the ice maker back up again, but until you deliver enough sediment to build that carpet in front of it, you can't advance. And that's a scary thing. That suggests that the climate dial is not something you simply adjust and get the glacier you want, but the history is really important.
Are there any estimates of how long Lake Russell existed and then was used that Black Lake spillway?
Well, again, the only estimate I know of is the one from Tim Walsh and Josh Logan, who said that when they saw barbs that they thought were from Lake Russell and Lake Bretts, they never saw more than about 20 of them. And if they're annual, that's 20 years. Now, there's certainly more barbs than that because we know the sections they looked at are incomplete. But how many more? Excuse me.
Gotta watch that arm waving.
Yes.
I have a question, and maybe other people still do, but has any retreat of the lobe of an ice sheet on this scale and that sort of rate, that's not been observed in modern time, has it?
I don't know. I'm not that familiar with literature. I've done some reading on Icelandic Piedmont glaciers, where there are retreats that I don't have scale on these, where there is significant retreat, and it's clear that in some cases good preservation of the base of the ice sheet is because the ice has stopped moving in that area and melted, and it's not been active ice retreating over and exposing the undisturbed base.
Right. Anybody else? How about one more round of applause?